In this video, we will be discussing angular and linear velocity and how to evaluate and find them in real life applications. So, angular and linear velocity, there's actually two things going on here. And sometimes you will actually see angular and linear speed instead of velocity. And when you get into physics, there is a difference between a speed and velocity basically, but for the sake of what we are doing right now, we are going to just interchange that together, interchange velocity and speed together. So first we're going to do angular velocity. Angular velocity is exactly what it says. It is basically how fast an angle is moving or turning around a circle. So if you look in this case, the angular speed is like, let's say you have an initial side and you have a terminal side, and you're wanting to know how fast that terminal side is moving around. So you're talking about this angle, how fast is it turning around the center basically. That is the angular speed. How fast is that going? Linear speed is, let's say there is a person on the edge of this circle. The linear speed is how fast is the person turning around the circle. So if the person is really close to the center, he's going to be turning really fast. The farther away from the center the person is standing, the slower he is going to be turning. So the radius is taken into account only with linear velocity. So basically, if you take the angular velocity and you multiply it by the radius, you'll get linear velocity. So angular velocity formula is basically, looks like a W. Angular velocity is represented like a W. And it is the angle of the measure in radians, always, divided by time. So if he goes 50 radians per second, that means he made it 50 radians around every second. So time is always going to be in the denominator, because if you think of it like as in miles per hour, kilometers per hour per second, time is always going to be. So angular is always going to be radians per time. So radians per minute, radians per hour, radians per second, radians per days, it doesn't matter, but the unit of measure is always going to be in whatever the radian is divided by time. The linear velocity, that is actually where you get miles per hour, kilometers per second, that we're used to seeing in the real world, because the linear is where you actually take a person or some type of object and you place them on the edge of the circle, so it matters of how big the radius is, and you find their speed. So think of it as distance divided by time, which we just learned in arc length, that the arc distance is S equals R times theta, if you remember that. S equals R times theta. That is the distance around a circle. So if you were to take that and divide it by time, then you will get the linear velocity. So you don't necessarily have to worry about this necessarily so much. If you just basically, if you take, there's one or two ways you can do it. Take the angular velocity and multiply that by the radius. Angular velocity, and multiply that by the radius. That is the same thing as finding the arc length and dividing it by time. It is the same exact thing is happening. So you can either find the arc length divided by time, or you can find the angular velocity and then multiply by the radius. It actually is going to give you the exact same thing. So let's actually attempt this problem. The second hand of a clock is 10.2 centimeters long. That is the radius. Find the speed of the tip of the second hand. So the second hand is, if you think of it as the minute hand, correct? So if you think of it in terms of the angular speed first, so think of it, figure out the angular velocity. How fast is this hand turning? Well, it's the minute hand. It turns 2 pi radians, right? Because 2 pi is one full thing, right? Minute hand. It does a full 360 degrees in 60 minutes, correct? But remember, it has to be in radians. Well, 360 degrees is the same thing as 2 pi. So the angular velocity is 2 pi radians every 60 minutes. That is the angular velocity. It goes one full circle every 60 minutes. Now, to find the linear, we are going to take the angular and multiply that by the radius, which is 10.2 centimeters. Radians goes away the moment that you actually put a unit of measure in it. So in the calculator, 2 times pi times 10.2 and divide that by 60. And the linear speed is that the second hand, well, let's guess it's actually 0.7. It is going 1.07 centimeters per minute. So again, to find the angular speed, you first need to find the angular speed. How fast is the angle moving? And then you're going to multiply that by the radius. And again, since it's a clock, we know that it makes one full rotation every 60 minutes, which is 360 degrees, but we have to have it in radians. So that is why it is 2 pi. So let's do this example. Angular speed. A lawnmower makes 1.2 revolutions per second. They want it in radians per second. So revolution, if you think of a circle, one revolution is if you're starting and you're going literally all the way around one time. It has one revolution. So 1.2 revolutions per second. So here's what we have to do. We know that one revolution, one time around a circle, is 2 pi radians. That is always going to be the conversion factor. One revolution is always 2 pi radians. Now that we use that conversion, revolution and revolution cancel each other out. And so therefore, 1.2 times 2 pi is going to be 7.54 radians per second will be our answer. So that is the conversion factor. Anytime you're given something in revolutions, you need to change it to radians. So if you have revolutions per minute, you need to change the radians. You need to know that one revolution is equal to 2 pi radians. So now we're going to take all this and kind of combine it. A car is moving at a rate of 50 miles an hour. The diameter of its wheel is 2.5 feet, which means we need to automatically figure out what the radius is. First thing we want to do is find the number of revolutions per minute that the wheel is rotating, and then we're going to find the angular speed. So we know the linear speed. And we know the radius. So we know that the linear speed is the angular speed times the radius. The farther out the radius, the slower person's going to go. So we know the linear, we know the radius, we need to find the angular speed. So we're actually going to find number 2 first. That was backwards. That actually should be first. That should be second. Okay. So linear speed is 50 miles per 1 hour. But here's our problem. The radius is in feet. The linear speed's in miles. So the first thing I'm going to do is I'm going to go ahead and switch from miles to feet. I could go from feet to miles. It doesn't matter, but that's just going to be a really small number. So I'm just going to go the opposite way. So I know that 1 mile is 5,280 feet. So now I can actually go in feet per hour. So therefore, 50 times that. So I know is in miles per hour, and that is the angular speed times the rate. That's not miles, sorry. Feet. Times 1.25 feet. So I'm now going to divide by 1.25 feet. And so that divided by 1.25 is going to give me 211,200. And that is automatically going to be, because the feet are going to cancel, so that is going to automatically turn into radians per 1 hour. That is my angular speed. Now they want to know what that is in revolutions. So, per minute. Okay. So 211,200 radians in 1 hour. Well, we know that 2 pi radians is 1 revolution. So therefore, radians cancels. So I now know, I just need to make sure I put parentheses around that. So 211,200 divided by parentheses 2 pi, because both the 2 and the pi are in the denominator, is going to give me 33613.5 revolutions per hour. But I need it in per minute. So now I know that 1 hour is 60 minutes. And I've now canceled the hours. And I now have revolutions per minute. So I do that and divide that by 60. And I will get 560.2 revolutions per minute. So that means the car is rotating 560 times every single minute at the speed of 50 miles an hour. So I want you to attempt to do this problem on your own. Pause the video, attempt to do this problem, and then resume to see the answer. Okay. All right. An ant sits on a CD at a distance of 17 meters from the center. Automatically radius. If it sits there for 42 seconds, it travels 913 centimeters. So basically, he is 17 centimeters away. And if you go for 42 seconds, it's going to travel 913 centimeters. Okay. So what is the angle at which the ant turned through in radians? Okay. So we know the angular velocity automatically, because angular velocity is radians per time. Now, so we've got to figure out what is the radians. So here's what we do. We know that it travels 913 centimeters, and we know that the radius is 17. So automatically, I know The distance it traveled was 913, and we know that the radius is 17, so we've got to find theta. So therefore we know theta is 53.71 radians. So therefore the angular velocity is going to be the radians divided by time. So number one, we got the answer of 53.71 radians. It wants to know what the angle was that it turned. So when a distance of 913 centimeters, the radius was 17 centimeters, so we were able to find the radians. We found the angle. That was number one. That's what we did here. Number two is what's the speed. The speed, oh no, you know what? I need to do this all again. Okay. Now, for the next practice, I want you to pause the video, attempt to do this on your own, and then I want you to resume to see the answer. Okay, so we have an ant that sits on a CD. The distance from the center, so this is automatically the radius. It sits there for 42 seconds. It travels a total distance of 913. Number one says, what is the angle that it turns in radians? Well, we know that it travels a distance of 913 centimeters, and the radius is 17. So automatically, we are going to use the arc length of r times theta. We know that it traveled 913 centimeters, and we know that it is a radius of 17, and we need to find theta. So when you divide that, you get 53.71 radians. That is the answer to number one. Now that we know the radians we know the angle at which he moved, and we can now find how fast he moved at that angle. What speed was he at? Oh, we're going to go to number three next. We now want to know the angular velocity. The angular velocity in radians per second means we are going to do the radians. And it took him 42 seconds to make it that far. And so 53.71 divided by 42 gives you 1.28 radians per second. That was number three. Now we can go to number two. Now we're wanting to know, since it said centimeters per second, that is the linear velocity. So basically, if you take that and multiply by the radius, you will get how fast the ant traveled. The ant traveled 21.74 centimeters per second. That is number two. And then RPM is going to be taking the radians per second, and we have to do a conversion. We know that 1 revolution is 2 pi radians, so that will cancel the radians. And then we know that they want it in minutes, so we know that 60 seconds is equal to 1 minute. If second was on bottom, then I got to put seconds on top in order for them to cancel. Now everything is canceled, and now I'm going to multiply the 1.28 times 60 and divide that by, don't forget to put parentheses, because both the 2 and the pi are in the denominator, and you will get 12.22 RPM. So the CD turns 12.22 revolutions per minute. In this case, if you would like to pause the video and attempt to do this problem, I'm going to go ahead and solve it out for you. Wheels are 3 inches in diameter, which means the radius is 15 inches. The wheels rotate at 150 RPMs. Okay, that is automatically angular velocity. So I'm going to go ahead and switch that. So 150 revolutions per minute. I know that 1 revolution is 2 pi radians because I have to get angular velocity in radians. It always has to be in radians. So that cancels, leaving me 300 pi radians per minute. Now I'm going to multiply that by the radius, which is 15 inches. So 300 pi times 15 is 14137.17 inches per minute. Is how fast she is traveling linear. That's technically that's the answer, except they want it in miles per hour. So what we do is we are going to take this and do nothing but convert. So 14137.17 inches in minutes. 1 minute. Okay, I'm going to go ahead and convert inches into miles first. So I know that there's 12 inches in a foot. That cancels the inches. And I know that there are 5,280 feet in 1 mile. All right, we have miles. Great. Now we need to go from minutes to hour. So if minutes are on bottom, then I got to put minutes on top. There are 60 minutes in 1 hour. Okay, minutes have now been canceled. So everything's canceled except for miles on top. Everything's canceled for hours on bottom. So I'm there. So here's what I have to do. I got to multiply everything across first. So 14137.17 times 60. Now, I had to divide that by 12 and by 5,280. So make sure that you put parentheses, the fact that you're multiplying by 12 and 5,280 feet in the denominator. So make sure that you put parentheses around these two. And when you do, you should get 13.39 miles per hour. So she is traveling a little over 13 miles an hour riding a